already. So let me just okay. So we start here first with the aluminium industry. All right. Any questions or concerns before we move into the topic? So as I go through something, I want you guys to just drop a 1 in the chat if we're ready to move on to the next concept. I'll let you know when that should occur, right? So if I ask if you guys are ready to move on, just drop a 1 in the chat. If we're ready to move on. If we're not ready to move on or an issue or a concern, all you have to do is raise your hand and go ahead with the question. All right. So let's go. So the aluminium industry. Now, with all industries, right, what we're looking for as chemists, right, are our precious materials, right? So the precious materials that we're looking for in this case this precious material would be aluminium, right? Now, aluminium doesn't naturally occur as Al in nature, right? As solid aluminium. Aluminium is a highly reactive on its outer layer, right? Easily oxidizing to produce aluminum trioxide, right? So we should remember that. So our aluminium oxides are easily made. So with that, noting to its reactivity, it can be found embedded in other sources, right? And what we're trying to do is break off all the impurities. Impurities really and truly are things that we don't want. So we're trying to separate the aluminium which we want from what we don't want. All right. If you guys will do a geology course, right? Because I remember some of this from geology, right? So you'll be looking at different minerals if you choose to do geology, right? And some of these minerals are the things that we would now extract from the earth, right? And as chemists, we develop different processes that will actually extract what we want from the source, right? So what we have here, the primary source of aluminium is bauxite, as we should know, right? So bauxite is a primary aluminium ore, right? And it's really composed of hydroxides, right? Including gibbsite, right? Which is the trihydroxide, right? Bohemite, right? Which is really and truly gamma aluminium oxide hydroxide. Diaspore, right? Quartz, hematite, rutile, right? These different things, right? We can find aluminium embedded in some of these materials, right? Hematite and rutile are found along with gibbsite, bohemite, and this diaspore. All right. So these are some things that we'll look at. So using the Bayer process, right, to purify the ore, and then the Hall-Héroult process for smelting aluminium oxide and producing aluminium metal. All right. So we're going to be looking at the purification. So once we get the minerals, our first aim is to purify it using the Bayer process. And after we purify it to the greatest extent that we can industrially, we will now try to smelt the aluminium ore to produce pure aluminium metal using the Hall-Héroult process. All right. So that's really and truly there. So we start off with the Bayer process, the purification of bauxite. So we're going to be using bauxite because it's a primary ore. Any issues so far? So once in the chat if everything is okay. If you have a question, go ahead. I'm expecting to see a 1 from everyone, but if there's a question, just go ahead. All right. So 2 persons are fine. Daniel Divine, is everything okay? Anushka is okay. Austina is okay. All right, lovely. Ashanti is okay. So let's move on. So the overview. So the Bayer process is used to refine bauxite ore into aluminium oxide, or what we call alumina. Right? Aluminium oxide or alumina, right? Is what we're going to smelt in the Hall-Héroult process, right? So bauxite typically contains iron oxide, silica, and titanium dioxide as impurities, right? So those are some of the impurities that we can see there. So when we talk about the hematite, that is iron oxides, right? Rutile is a titanium dioxide, right? Silica, we know, is silicon dioxide, right? So you guys should know these oxides and stuff like that. This should be fine, all right? So here's the process now, right? So we're starting first with crushing and grinding. So we get the bauxite ore out of the ground, and now we have to increase its surface area. In science, we say increase the surface area, but really and truly, we're crushing and grinding it, right? So bauxite is crushed and ground into a fine powder to increase the surface area for a reaction to occur in a more uniform and quick manner, right? Makes sense. So we crush it and we grind it. Then we have what we call digestion. So the powdered bauxite is now treated with hot concentrated sodium hydroxide solution at temperatures between 150 to 200 degrees Celsius and at high pressures about 5 to 35 atmospheres. No, I'm not sure who was here in September when I just started chemistry unit 2. But when we talk about reactions, what must we have? We must note 4 things. We need to know what we're reacting, the reactants. We need to know the product, right? So the reactants, the product. We need to know the conditions, and we need to know the reagents, right? Apart from our primary reactant. So what are we putting into the reaction? That is bauxite. What is our reagent here? Sodium hydroxide. What are the conditions? 150 to 200 degrees Celsius and at pressures of 5 to 35 atmospheres. Full stop. We need to know these things. What are we reacting? What are the reagents? What are the conditions? And what are the products? If you know those 4 things about all reactions, Unit 2 chemistry is surely a 1. Right? If you know those things, everything should be fine for at least Module 1 and Module 3. Alright? So the sodium hydroxide dissolves the alumina and forms soluble sodium aluminate. Right? A little complex ion there. Alrighty? The iron oxides, silica, and other impurities remain insoluble, forming the red mud, right? So that waste product there. So the red mud, I'm about to say complexion, but the red color is from hematite. We know already from CSEC, not even CSEC, but Unit 1 chemistry, that iron 3 is a red color. The iron oxides now give it that kind of reddish color. Right? Along with some other impurities, of course. And the chemical reaction for digestion is presented here. We react now our oxide, right? Our entire oxide here, right? With the sodium hydroxide solution, which is the water and the sodium hydroxide, and we end up with sodium aluminate. Or in this case, it is sodium aluminium hydroxide, tetrahydroxide, right? Its ionic form would be the aluminate, but in this case, it's sodium aluminum tetrahydroxide, all right? Or just hydroxide, because once you understand that there's 2 of these, then you should be good, all right? So the sodium and the aluminium has a valency of 3, sodium has a valency of 1, therefore there must be 4 hydroxides. Right? So you don't have to say the tetra, right? If you understand valency already, which I will assume that you understand. All right. So we're moving on from there. Any questions or concerns before we move on from this? Daniel, is everything fine? All right. Not too much of a problem. So remember, the first thing in the Bayer process, that is what we're looking at. We crush and we grind to increase surface area. Then we react with the concentrated sodium hydroxide solutions at 150 to 200 degrees Celsius at 5 to 35 atmospheres. And what we must get is sodium aluminate, or what we call sodium aluminum hydroxide. All right? So working from there, go ahead. Mm-hmm. Mm-hmm. What's the goal? All right. So the goal here, what we're remember, right? What we're trying to do in the Bayer process is to purify. So it's one step in the purification process, or what we call the Bayer process, right? So notice here, right? What we're trying to do is isolate the aluminium, right, in a complex ionic form, right? So what we're doing, we're reacting with sodium. Sodium is high up in the reactivity series, not true? C-sec chemistry, right? So we're trying to do now, we're trying to displace the aluminium, right? Well, not really displace the aluminium. We're trying to capture the aluminium and displace the other impurities like the hematite and rutile, right? We're trying to displace everything else. So notice now that we have the aluminium in the form of sodium aluminium hydroxide, while the iron oxide, silicon, other impurities remain insoluble. So what we're trying to do, the digestion now, is breaking up the bauxite, isolating the aluminium in a complex, and then allowing for all the other impurities to remain insoluble. So it's kind of purification, right? It's really and truly that. Did I answer your question? All right, no problem. Then we have clarification and separation now. Now we have a red mud slurry, right? Meaning that we have a suspension, right? Suspension, we have a suspension, we have a solution with some things being solid, insoluble in solution, right? So we have insoluble impurities, or the red mud, are separated from sodium aluminate solution by sedimentation or filtration. Now there's a reason why we do module 2 before we do module 3. And really and truly, we never have to do module 2 before module 3 because this is C-sec, right? So when we're dealing with these suspensions, remember suspensions from section B of the chemistry C-sec chemistry syllabus. Suspensions, because the solids are so huge, you can just let the solution sit and then it will settle at the bottom through sedimentation. Or if we want to move quickly, we can use gravity filtration, or we can use vacuum filtration. All right. So we're using separation techniques, or we can use desiliconization, right? Which is what happens when there's a high silicon content in the Bayer liquid, right? Bayer liquid just means the product after the Bayer process, all right? And what we're trying to do is get the DSP here, right? So the desiliconized product, right? Or basically our clarified or purified product should be whitish like this. If it is reddish like this, now we know that there's hematite present. We know that there's rutile present. We know that there are impurities present if it looks like this. We're trying to get it to the whitish color. All right, we're trying to separate it properly. All right, so we're using sedimentation or filtration, right? And that is basically there, right? That's a third process. So remember, we're crushing and grinding. Then we're digesting using hot concentrated sodium hydroxide, right? And then we're clarifying it and separating it, right? So we're trying to purify it down, right, properly. And then the last process now is precipitation. So the clear sodium aluminate solution is cooled and then seeded with aluminum hydroxide crystals, right? This causes precipitation of aluminum hydroxide and the chemical reaction for precipitation. Go ahead. Okay, meaning now what we want is aluminum hydroxide, right? Since we have a concentrated solution of the sodium aluminum hydroxide, right? What we do is put some seeded, means so we add some crystals of aluminum hydroxide in it to start the precipitation. Now, remember chemistry unit 1, module 2, solubility product, common ion effect. We increase the concentration, we add aluminum hydroxide crystals into solution, right? Remember that thing from chemistry unit 2, from chemistry unit 1 rather. We add a common substance into solution to decrease the solubility, right? So what we'd want is for the crystallization, right, of the aluminum hydroxide. So since we already have a very saturated solution, we add some solids in there now, and then everything else will start to crystallize around those small crystals that we add to the solution, right? So causing precipitation, and the chemical reaction occurs here where our sodium aluminium hydroxide becomes aluminum hydroxide and sodium hydroxide. So we're separating the hydroxides there. All right. So this is the precipitation. So we cool it now until it's super saturated. Then we add aluminum hydroxide crystals to it to precipitate out aluminum hydroxide out of the sodium hydroxide solution. One who reads and admires the chemistry can see that all of these chemical principles were taught before we've reached here. All right? We must not only gain the knowledge, but we must use it. All right? So let's move on. Calcination is going to sum up our process. The precipitated aluminum hydroxide is heated in rotary kilns, right? So they're basically blasting a huge amount of, well, a huge temperature, right? Blasting the solution with the substance with huge amounts of temperature, right? Or very high temperature rather, right? And it continues to rotate. So it spins as it gets heated, right? So we do it in rotary kilns, right? Or fluidized bed calciners, right? At about 1,000 to 1,100 degrees Celsius, right? To remove any water. This reminds you of gravimetry. Volatilization process of gravimetry. This is a separation technique. All right? Where we heat it to remove all water, right? To now isolate aluminium oxide, which is alumina. And now, isn't that the process? Isn't that the reason why we started the Bayer process? To get alumina. And that is there. Calcination is there. All right. So when you see calcination, you're like, so where is the calcium? It's not that calcium is added, right? That was my full question, when my chemistry teacher went through it, right? She was just explaining, doing the most. After she done explain topic, I was like, so where's the calcium? But it doesn't contain anything like that. So we're just heating, right, to remove all the water. Why is it calcination? Because it's probably because we have them in calciners, right? That's the name of a apparatus that we use. So it's called calcination. But yeah. So that is that. So that's a Bayer process. We grind and crush the bauxite, then we digest it. We try to separate off most of the impurities, then we clarify and separate, then we precipitate, then we calcinate, and we're done. We end up with alumina, which is aluminum oxide rather. All right. So that is what we have there, and then we move on now to the Hall-Héroult process, which is the electrolytic reduction of alumina. All right. Ready to move on? Is everything okay? After the Bayer process, yes, after. So after the Bayer process now, we have alumina. That is still not aluminium. So we need to now do something to the alumina to get aluminium. And the Hall-Héroult process you have discussed already in CSEC. All I need to do now, my job is to really jog your memory, right? So let's go. Any questions or concerns from anybody else before we start this process? Let me not take any information for granted. Everybody's fine so far? All right. Electrolysis, right? So we're setting up an electrolysis reaction, right? So alumina is dissolved in molten cryolites, right? Or sodium aluminum hexafluoride. Trisodium aluminum hexafluoride, which is cryolites. Go ahead, Daniel. Oh, this is not there. It is currently being recorded, right? So alumina, right, is going to be alumina rather, right, is going to be dissolved in molten cryolite, right, to lower the melting point right, to about 950 to 1,000 degrees Celsius, right, and improve conductivity. All right. So it's the same way in which the conductivity of water is improved when we add a salt. This is a salt that we're adding the thing to, right? To decrease the melting point. All right. Same concepts. The electrolysis occurs in a carbon-lined steel tank, right? The cathode, right? With carbon anodes dipped into the molten bath. So this is what we must provide. Now, please be reminded, for every single reaction we go through, you must be able to draw these diagrams and annotate them. At no point should a chemistry student, unit 2 student in my class, not be able to draw this. At no point. You must be able to draw this. So you make a crude diagram of it, right? So you know where everything is. Label the cathode, label the anode. What the cathode make out of, what the anode make out of. We need to know these things. What does what the tank make out of? It's a steel tank, right? So you guys need to be able to label and draw and label the diagrams. Alright, so we're working a simple electrolysis setup, right? So that's fine. Alright. So the cathode is a carbon-lined steel tank. The cathode is a negatively charged electrode, and the anode is a positively charged electrode. Lovely. Any questions here? Any concerns before we move on with our lives? Guys, please be reminded, if you have a question, ask it. Alrighty. The electrolysis reaction, now I provide this detailed diagram here, so we can read it. Alright, but really and truly now, right, what we're looking at now is the fact that a direct current is being passed through the molten bath, causing the aluminium cations to migrate to the cathode, right, where they gain electrons, right? Remember this: oxidation and reduction, right? So we gain electrons at the cathode then and form aluminium metal. The oxygen anions now migrate to the carbon anodes, where they lose electrons and form carbon dioxide. This chemical reaction, right? This is the chemical reaction for electrolysis here on the right. So they have the molten aluminum oxide, and we're trying to separate them now using electrolysis. Right, so in the industrial design of the electrolysis cell, the method of collecting aluminium and dealing with waste gases are ignored right here. Right, so we don't look at the collection really and truly here. We just look at how we separate them, and we don't look at the fact that, okay, carbon dioxide really and truly should be produced. Right, so what's gonna happen there? This diagram says oxygen is produced, but some carbon dioxide is produced as well, right? Because this is a carbon cathode, therefore carbon dioxide will be produced. All right, so we're working on this. Does everybody understand the diagram? Does anybody have a question about the diagram that they would like to be answered? And yes, this too you must be able to draw and label and explain. You guys should remember how conventional current, right, versus regular current. You guys should remember those things. The fact that it makes one full circuit, we're looking at the net ion movement and net electron movement and stuff like that. Where reduction occurs, where oxidation occurs. If they ask you to write the half reaction for each the process, you must be able to do so as well. Alright? So they could speak about the electrolysis of the aluminium, right? Provide the half reactions, both half reactions, oxidation half reaction and reduction half reaction, right, for the electrolysis of aluminium oxide. 4 marks. You must be able to do it. Alright? So working off of that, any questions or concerns? So I'm noting the things that you guys need to know about it, So if you don't remember what oxidation and reduction really and truly is and how to write the reactions and how to combine the reactions, I beg you go back to chemistry unit 1. Or if you don't do the chemistry unit 1 yet, I beg you go back to CSEC, because CSEC students should be able to do this as well. Alright? Because remember, as I said, I'm jogging your memory. This is done in CSEC. Alright? It's only now we probably look at it and try to use more complex terms with it, but more or less we do this already. Alright? So let's move on. So the energy consumption and environmental impact now. We have to look at the impacts of this industry on the environment. So the Hall-Héroult root process, right, is highly energy intensive due to the high temperature required. What we say, we need around 950 to 1000 degrees Celsius, right? That's a very large amount of electricity would be required, right, in order to create those temperatures, right? Additionally, the carbon anodes are consumed, releasing carbon dioxide, contributing to the greenhouse gas emissions. So when we reach atmospheric chemistry and we start speaking about the degradation of the ozone layer and how the greenhouse effects works, right? And looking at photochemical smog and all these different types of things, we'll tie in all the different emissions that we have there, right, from each industry. And this is why I do all the industries first before I do the first topic in module 1, because this is important in explaining that topic, right? Producing aluminum from bauxite ores requires large amounts of energy, which accounts for a high cost and environmental impact of aluminum production, right? This has led to research into reducing energy consumption and finding alternative, less carbon intensive methods of production. Now, remember, not only are we doing industrial chemistry, but we're also focusing on green chemistry. Yes, we need aluminum for all these different things. We're going to discuss what we use aluminum for, by the way, in the coming slides, right? But we need to understand the impacts of these industries on the environment. Not only on the environment, but on the consumer, right? So if we continue to use high energy intensive processes like the Hall-Héroult process, right, especially in the Caribbean, right, what does that mean for our energy consumption, our energy bills? Energy consumption in the Caribbean is ridiculous compared to some regions. Ridiculous, right? So if we intend to completely industrialize, right, and make the best use of these minerals, right, how can we safely produce them, right, at an industrial rate, reducing the energy consumption that we have, right? What we need to understand is Le Chatelier's principle and use chemistry in order to figure out these processes. So this is what chemists sit down and do, industrial chemists. If you'd like to become an industrial chemist or a chemical engineer, these are the processes that they deal with, right? They look at them and then figure out, okay, is it better to use a potassium ion or to use something sodium or lithium in nature? Like, what would reduce our energy cost? This is what they sit down and do, right? Figure out the issues in our processes and try to make them better. Alright? But you guys need to think this way when it comes to module 3, right? Not only, okay, carbon dioxide is produced, therefore greenhouse gas, full stop, global warming. That is not an all-around answer. They need you to understand the impacts of the energy consumption, environmental impact of these industries, right? So you need to look into those things and think about all the different aspects that may be there, right? Now, the property of aluminium, right? We're looking at aluminium itself, the physical and the chemical properties of aluminium. We know that the physical properties, right? We know that it is lightweight. It's a third, right? It is 1/3 the density of steel. It's very, very light compared to other metals, right? It's very strong as well, right? So despite its lightweight, aluminium, right, can be alloyed with other metals, right? For example, in steel, right, and create very strong structures, right? Corrosion resistant as well. Remember that aluminium is extremely reactive. So when it reacts with aluminum oxide, it produces that protective layer. This is also CSEC, right? So it protects aluminum from harsh environments, right? Reducing oxidation and corrosion, right? Remember the properties of metals from CSEC: ductility and malleability. Aluminium is easy to shape and form, allowing it to be used in various manufacturing processes. It has good thermal and electrical conductivity because it is a metal. I won't explain anything further there. We should know that. It is non-toxic and it is also non-magnetic. Right? So aluminium is actually no. Aluminium is not toxic, but that does not mean that we should go and eat aluminium. Aluminium is found in half of the cornflakes that you eat. Aluminium is found in some of the roll-ons that you use as well, like the deodorants in your arm, right? And it can be absorbed by the body and it may or may not produce issues, right? So not because it's a non-toxic meat, so we're supposed to be consuming or interacting with so many metals on a daily basis, right? So it really and truly makes it suitable for medical applications and used in food as well, but that does not mean that it's okay to eat large or copious amounts of aluminium. Too much of one thing isn't good, right? It's also non-magnetic, so that's why we can use it in medical applications and stuff like that. So when we use the large machines, right, when the medical physicists would use these large machines in the hospitals, right, aluminium implants and stuff like that won't be affected as much, right? Because remember, it's not diamagnetic or paramagnetic to the degree, right, that it would be dangerous. All right. Diamagnetism and paramagnetism is discussed in module 3 of unit 1 chemistry. All right. But those are the general properties. Now the applications, now we use them in aerospace and aviation, right? Because of its lightweight nature, we can use them in aircrafts, right? Using for aircraft components, right, such as fuel gauges, wings, and landing gear, and it's corrosion resistant, right? That's why it's crucial for aviation. All right. So it's important there, especially when it comes to radiation and stuff like that. When you fly in the stratosphere, right, you are going to be bombarded by so many rays, gamma radiation, alpha radiation, stuff like that, right? So generally, let's not divide them up. Solar radiation in and of itself, right? And continuously moving through the atmosphere, right, at different layers that may contain different levels of humidity, right, that may corrode different metals. But because aluminum is corrosion resistant, that's why we kind of use it better for aviation, right? It's a little bit better suited there. It's used in the automotive industry. As we can see, many cars are made out of aluminum for the most part, right? So the wheels themselves, not tires, because somebody asked me last year whether or not if I ever see a tire make out of aluminum, but tires and wheels are two different things, right? So engine blocks, wheels, body panels, right, of different motor vehicles are made out of aluminum for construction and architecture as well, right? So remember, it's lightweight, it is strong, and it's corrosion resistant. So most of the structures that are outside, right, and are at the mercy of the weather itself, most of those structures are made of aluminum because of its strength and corrosion resistance. All right. Electrical and electronics, right? So it's used in these fields as well for power cables, transmission lines, transformers, electronic heat sinks, these different types of stuff, electricity wells, etc. Right? We use aluminium for this because of its high conductivity and its high thermal conductivity as well, right? Now, electrical and thermal conductivity. Alrighty, so these are some of the reasons why we use them, right? And then we're on to the detrimental effects of aluminium, right, on the environment, the aluminium industry rather, on the environment. Are there any questions or concerns as it relates to the uses or applications of aluminium? Any issues? Any issues? Questions? Or if you want to say something, any statements? Are you guys good? Just drop a 1 in the chat if you're good, if you're okay. And if you have a question, go ahead. Sanoshka is good. Janaya is good. Alright, so everybody seems like they're fine so far. Alright, I think this means that the PowerPoint is comprehensive. Alright, so the detrimental effects now. Bauxite mining and land degradation now. First of all, if you mine bauxite out of your ground, nothing else can grow. That's all. That's the first thing, right? So, right, not only are you completely and utterly destroying the habitats, right, but we end up with loss of keystone species and unraveling the web of biodiversity in the area, right? So we have stuff. Okay, so we have to mine the bauxite, right? Therefore, if it is covered by a large swaths of forest, right, we have to deforest the area. So deforestation is occurring there, and we reduce the biodiversity as it's stated there. First, students of Unit 2 biology should understand how this affects the wildlife, right, and the ecosystem diversity in regions where we have bauxite mining, right? It is important. So the loss of ecosystem, the displacement of wildlife, right? So even for example, right, I live in Jamaica, therefore my examples are Jamaican. Right, for example, right, different agencies or companies, I won't be too controversial as this is definitely recorded, right, would love for the opportunity to mine in the cockpit country. No, the cockpit country is not only one of the most biologically diverse areas in Jamaica, but in the entirety of the Caribbean. All right, but it is rich in bauxite. So the moral dilemma now is, do we tear down literally the most biodiverse place in the entire country just for bauxite? Or do we let it stay? Right, so that is really and truly the question. Now, that question may seem very obvious to you, but it's not very obvious to some persons, right? The answer may be very obvious to you, but it's not obvious to some persons, right? So we're looking at that. Even the cockpit country is made up of prairies, so different hills and stuff, right? It is so that biodiverse that one hill over here so may have a species of bird, and 5 miles away there's a completely different species of bird in the same family. That's how biodiverse and species diverse the place is, right? But it is rich with bauxite. So let's see what happens in Jamaica in the coming years, right? Because we don't know what will happen. Soil erosion and contamination is important as well. So the removal of vegetation and topsoil during mining leads to soil erosion and can cause sedimentation in nearby water bodies, right? For example, I think Yalos, there's like something in St. Thomas, a lake filled with waste, bauxite waste, right? Killing all aquatic life in the region there, right? So that's important. Go ahead, Daniel. It spans through Trelawney, St. James, and a piece of northern St. Elizabeth. It's really huge. It's really huge. I I can't give you the exact, size, but I think it spans through multiple parishes. All right, but we have something like that there, right? So soil erosion contamination is important as well. So we can sedimentation into nearby water bodies, right, can now affect aquatic life there, and water pollution, of course, because I don't know why people feel like when they go through the Bayer process through digestion and end up with all these pollutants that they should dispose of it in water bodies. If you do so now, you're going to contaminate the water sources, right? Introducing chemicals and heavy metals, right, that were used in extraction. You're going to be introducing it into the wildlife. No, not only are you destroying the fish populations, right? But we remember bioaccumulation from Unit 2 biology so far. If the fish start to consume these heavy metals and chemicals, and then we start to consume the fish, right, that becomes a health risk. All right. So looking at stuff like that. For example, fish often contain a small amount of mercury, right? And in very polluted areas, they can contain small amounts of plastics, right? And iron and cobalt and all these different things that you place in the water. All right. So the food itself will continue to be contaminated there, right? Red mud waste from the Bayer process as well, right? The Bayer process produces a large quantities of milk of the red mud, right? The waste product containing iron oxide, silica, and other impurities, right? Heavy metals are present in this mud, right? So it's typically stored in tailing ponds, right? Which pose an environmental risk if it leaks or dam fails, right? Or a dam fails, right? So they normally just heap it up in one huge area, right? So if you were to say have a flood, or there was supposed to be a crack in the infrastructure, then all of this will just be let out across the surrounding areas, killing everything in its path. Alright? We have soil contamination and water contamination here as well. The red mud can contain caustic residues of sodium hydroxide. Remember that sodium hydroxide it can burn the skin, it can burn living matter, right? If improperly managed, it can leach into surrounding soil and water, leading to contamination and affecting local flora and fauna. Flora is the plants, fauna is the animal life, right? Or the non-plant life rather. All right. Energy consumption, carbon emissions, notes the high energy requirements of the Hall Hill process, right? It requires large amounts of electricity to melt aluminum oxide and carry out the electrolysis, contributing to significant energy consumption. And then we have the production of the carbon dioxide from oxygen anions reacting with the carbon cathode, right? So it contributes to the greenhouse emissions and climate change, right? And also it has a source of energy, right? So the environmental impact is magnified if the energy of aluminum production comes from fossil fuels. Because yes, we require a large amount of energy for the electrolysis to occur, right? But how are we generating that electricity? Are we using fossil fuels? Are we using coal? Are we using petroleum? What are we using? Creating the energy itself to run this industry is another problem in and of itself. So not only is the industry a problem, the industry that we use to run this one is also a problem. Right? So everything just ties into itself, right? Making it worse and worse. Right? More worse. Right? So we're looking at stuff like that. So we have to really look at the sustainability as chemists. Yes, we know that aluminum is very important in modern life, right? But looking at the sustainable ways to carry out these things are one of the essential parts of what green chemists do or environmental chemists do, right? So aluminum is highly recyclable, right? And recycling aluminum requires about 5% of the energy needed for primary production. This significantly reduces environmental impacts compared to primary aluminum production, right? We know resource conservation. Recycling helps conserve bauxite resources and reduces the need for mining, thereby mitigating the associated environmental impacts. Right? So we're trying to mitigate those things. So we're looking at strategies to mitigate environmental impact, implementing sustainable mining practices. Right? So using sustainable mining practices such as land reclamation, reforestation. So when you cut down the forest, at least grow it back, at least plant back trees, right? Minimizing the mining footprint can reduce the environmental impact of bauxite mining, right? Managing the red mud waste as well, right? Developing innovative ways to use and treat the mud and reduce waste and contamination risks. Utilizing or reducing rather energy consumption and carbon emission, right? We can actually use renewable energy sources for the production of the electricity that we use in the Hall Herald process. And we can optimize the electrolysis process and use carbon capture and storage, which is CCS technologies that can mitigate carbon emissions, right? Encouraging aluminum recycling as well. Just encourage persons to recycle aluminum containers, etc. Alrighty? So that brings us to the end of the aluminum process, right? The aluminum industry, rather.